Well, welcome everyone. This is Debugging C++ Routines in GDB. My name is Zartaj Majeed, and I'll be kind of going over where we are in terms of debugger support for coroutines and what you can accomplish today, what is still pretty difficult, and what can help you deal with the difficult issues. And I'll give you one coroutine little program as an example. And then we'll probably spend about 20 minutes on a demo where I'll fire up GDB. Hopefully it complies, and I'll show you what we can do. All right. How hard is it to debug C++ coroutines in GDB? Well, first of all, debugging is hard. C++ coroutines are hard. And GDB is hard. So logically, debugging C++ coroutines in GDB is 3 times as hard. To give you a sense of the challenges you face when you try to debug GCC compiled code with GDB that has coroutines, there is a bug against GCC that's been open and unsigned since 23rd February 2021. And the person who reported it said, I'm itching to get into C++ 20 coroutines, and are very grateful for their implementation, but I'm somewhat put off by the apparent inability to inspect them from within a debugger currently. While looking for existing related GCC-specific issues, discussions, or commits, I found the following paper, P2073. This seems to at least confirm the current state that I was seeing. I can't tell if support for this is missing in GCC or GDB or both, but I figured I'd try finding out here first. So this was open against GCC. The bug report does have some updates in the last 4 years, but it's still sort of orphaned. Nobody wants to acknowledge it. Nobody wants to take responsibility. And there's a similar situation on the GDB side. You tend to get a runaround when you want to deal with some issues. Is it really still this bad? No. So things have improved a lot since that survey in P2073. I came across that pretty early on, but I'm sure anyone who wants to debug C++ coroutines using GDB will come across this paper. And it's a survey of the state of debugging coroutines at that time. And C++ coroutines were still relatively new in 2021 or 2020 when the paper came out. But the paper's author said, you can't inspect local variables, you can't see the coroutine parameters, you can't see the promise. I mean, there was just a litany of things. So now you can set breakpoints, you can view local variables, you can view coroutine parameters and examine a coroutine's promise type. So all of these things that are kind of standard for functions, they will work for coroutines. The challenge is the features of coroutines that are not typical of functions, in particular 2 of them. So one is coroutines can be suspended. They're no longer on the stack. How do you examine a suspended coroutine? So that's still a little tricky. The second is, since they can be suspended and they can come back onto the stack and start running, that means that they have a call stack associated with them, right? So every coroutine can be suspended at any time, and you may have a multitude of these coroutines that are suspended. But they all can come back to the stack and be executable, be running, just like any other normal function at any time. So that begs the question, where is the call stack for each one of these coroutines? And that's what's referred to as the asynchronous call stack problem, or, So what you would like to do is, you've got a bunch of coroutines, at any point, you would want to know like where the call stacks are. And this is a very difficult problem right now. There's been some attempts to solve this, but they, as far as I can tell, the current situation is that people have come up with solutions and sort of techniques that are very specific to their libraries or their applications. And there isn't like a good general solution out there. Okay, so let's start with a coroutine problem. This problem that I'm using is a very old problem. In fact, it's one of the, if not the original problem that was used to motivate coroutines. So if you know about the history of coroutines, they were proposed or invented, discovered by Melvin Conway. And Conway had a problem to motivate coroutines. Knuth, in his The Art of Computer Programming book, he doesn't say this, but I believe that he kind of simplified Conway's problem because he is a big fan of coroutines too. And he wanted to motivate coroutines very early on in The Art of Computer Programming. And so he came up with this problem that he felt sort of highlighted the special nature of coroutines for certain kinds of problems. Why would you want to use a coroutine for certain problems? So this problem was used to motivate that. A lot of problems that are used as examples these days are not really, they don't bring out the special nature of coroutines. You'll often see like generator examples, and you'll see some async, use cases. But from what I've seen, pretty much all of them can be solved in conventional ways, or you can use threads. And they don't really bring out, what's special about coroutines. Why would you even bother with coroutines? So I think Knuth came up with a good, simple example. It's a text parsing and transformation problem. And he uses coroutines as loosely coupled functions collaborating to solve a problem. So that was his take on coroutines. So as I mentioned, this is the reference for the problem. And here's the problem. Suppose we want to write a program that translates one code into another. The input code to be translated is a sequence of 8-bit characters terminated by a period, such as A2B5E, and at the end you'll notice there's a period. This code appears on the standard input file. By the way, this is a literal quote, so a lot of the terms that he's using are somewhat, anachronistic, but I'm sure that you'll understand what he's talking about. Interspersed with white space characters in an arbitrary fashion. So you can have intervening white space. For our purposes, a white space character will be any byte whose value is less than or equal to the pound sign or hashtag 20. The pound sign, Knuth uses it as a hex symbol, as a hex prefix. So, where you would see 0x, Knuth uses the pound sign. The ASCII code for space. And all white space characters in the input are ignored. So that's sort of the input side of the problem. What's the output side? The other characters should be interpreted as follows when they are read in sequence. So this is the non-white space. If the next character is one of the decimal digits 0, 1 through 9, say n, it indicates n plus 1 repetitions of the following character, the character after that, whether the following character is a digit or not. So the first digit you find, it's a count for the next character to be repeated. And a non-digit simply denotes itself. The output of our program is to consist of the resulting sequence separated into groups of 3 characters each. Until a period appears, the last group may have fewer than 3 characters. For example, A2, B5, so on, should be translated into A, and then because there's a 2, That's a count for the next character, which is a B. So that's going to be 3 Bs. Remember, if you see an N in the input, that's N plus 1 repetitions of the next character. So 2B turns into 3 Bs. Now down below, you'll see the output. And you'll see that the 3 Bs are actually broken up. There's an A, and then 2 Bs, and then there's a space, and then there's the third B. And that's because the output has to be in groups of 3 characters. And so on. So, I think that pretty much covers it. There are a couple of subtle notes. Notice that 3426F in the input does not mean 3,427 repetitions of the letter F. It means 4 4s and 3 6s followed by F. Why? Because the first 3 digit, is the count for the next character, which can be a digit or a non-digit. So the next character happens to be a 4, but it's just treated as any other character. And so 3 plus 1 is 4, so you need to output 4 4s. And then, you've got 2 and a 6, so the 2 turns into 3 repetitions of 6, and then the F is just an F because there's no count before that. If the input sequence is 1 dot, the output is simply dot, not dot dot, because the first period terminates the output. The goal of our program is to produce a sequence of lines on the standard input-output file with 16 3-character groups per line, except, of course, that the final line might be shorter. This is another sort of twist to the output. So not only is the output going to be in 3-character groups, but a line is limited to 16 of these groups. So the last line could have a smaller number of groups, but all the other lines should have 16 3-character groups. The 3-character groups should be separated by blank spaces, and each line should end as usual with the ASCII new line character hex A. All right. So Knuth but he presented a solution with coroutines. And remember, he's trying to motivate coroutines. And this is in the context of his textbook, The Art of Computer Programming, in which the programming language is not a high-level programming language. It's an assembly language called MMix. MMix is the unique and special architecture that Knuth invented for his textbook. It's a RISC-reduced instruction set architecture, and all the programs are in the assembly for this architecture. So that doesn't take away anything from the problem. The problem is great, as a motivational problem, and so we come to why Knuth thought that coroutines are special, or what was his interpretation of coroutines. So subroutines, or like functions as we would call them in C++, he said these are special cases of more general program components called coroutines. In contrast to the unsymmetric relationship between a main routine and a subroutine, there is complete symmetry between coroutines, which call on each other. He's referring to the caller-callee relationship between normal functions. That's what he means, or he refers to as a main routine and a subroutine. A subroutine is always initiated at its beginning, which is usually a fixed place. A coroutine is always initiated at the place following, where it last terminated. Such coroutine linkage is easy to achieve with MMix if we set aside 2 global registers, A and B. So the last paragraph is specific to his architecture. It's very interesting, but it has nothing to do with C++. So here's the solution. We're going to split the problem into 3 functions along input, output, and processing of single character items. There's going to be a function called nextchar to manage the raw input buffer. There will be a coroutine called in to parse input and provide a character item for further processing. And then there will be a coroutine called out, And its job will be to format a character item and print the output. In and out are coroutines working in tandem, as I mentioned. In is a generator that yields one character at a time. And out fills a group of 3 characters awaiting each in sequence from in. Next char is a subroutine. It's just like a regular function. It's only called by in. This is a C++ coroutine port of the original solution. I've tried to be very faithful to his solution, so I've used the same kind of naming, the same kind of general design, except it's not in assembly. It's in C++. Okay, so here's the in coroutine. So in C++, now I apologize that I'm not going to go into a lot of details of C++ coroutines because I kind of assume that, either you have decided to use coroutines for something, and so you will spend the time to understand how coroutines are written and designed, or you already know a lot, and you just want to see, what's going on with debugging and what are people talking about. So this is not going to be sort of an introduction to the coroutine, mechanism in C++. But I will point out the salient features. I just won't explain them too much. So a coroutine is a function, but it's a special function that has to have at least one of the special coroutine keywords. So that's either co-yield inside the body, or co-await, or co-return. So any normal function that has one of these 3 keywords is automatically a coroutine. And the return type of, the function return type of a coroutine function is very special. It's typically an object. It's typically a class. And we call it the return object. So here, I'm calling it inRO for in's return object. You can have normal types too, but it gets hairy, so we won't get into that. But here, in is a coroutine. Its return type is inRO, which I will show in a minute. But here's what's going on. There's a big loop, and in that loop, essentially, it calls next char to get the next character, and then it decides what to do with this character. So, on the left side, towards the end, is just checking, is this a digit or a non-digit, right? So if it is a non-digit, we know that we are just going to return this, that we're just going to yield this, right? Because it's not going to be a count. If we continue on to the right column, if that test failed, then that means that this is possibly a digit. And in that case, we set this variable count to its possibly valid value as a digit. And if it turns out that count is negative, that means it wasn't a digit. And so we yield it as a regular character again, and we continue every single time whenever we've reached our decision point. And in the third case, we now know that the character that we got is a digit, and it's a count for the next character, so we just immediately get the next character, and we yield it, and we keep on getting the next, we keep on yielding the same character that many count times. So we're sort of fulfilling the count specification at this point. What's the next char function? It has a buffer, 1,000 bytes, so it's like reading 1,000 byte chunks of input at a time. And it basically checks if the buffer has some characters available, something available, then just return that. If not, then refill it and just ignore any character which is a space or a controlled character that's towards the end on the right-hand side. So pretty straightforward. I have fgetS over here on my slide. It's a little older, but in the code that I'm going to upload, we use cin and getLine, so more C++. All right, so let's go to the out coroutine. This thing is now responsible for taking the character that is yielded by the in coroutine and then preparing it for output. And preparing it for output means that it has to form those groups of 3, and it has to keep track of how many groups per line there are so far. And it's also pretty straightforward. But what you should note is where it's expecting characters from the in coroutine. So first of all, how does it interact with the in coroutine? So the first thing that it does, last line on the left side, is that it calls in so that it has its return object that can be reused. Then on the right-hand side, it again enters into an infinite loop, and it basically co-awaits or awaits a value from the in coroutine. So the co-await lowercase n is awaiting on the return object of the in coroutine. And it's not strictly the return object, but it's what's called an awaitable. But again, those are details. I'll go over some of these details in a little bit. So the next 2 slides are, again, just part of the processing that it has to do. Each section is responsible for, either forming a group of 3 characters to output or keeping track of the line with 16 groups. For that, it calls the function finish line, which is in this little box at the bottom right. Okay, so here's one of the problems that every coroutine design has to face pretty early on, which is that since coroutines are supposed to be these equal partners, one of them, you don't have that hierarchical caller-callee relationship. So, but something has to run first. And that's sort of one of the design decisions that you have to make with coroutines. In this case, we've got 2 coroutines, in and out. We're going to go ahead and start with out. And then it will need to await a character from in. So the first call will be to out, and it'll start executing the body of the out coroutine, and it'll reach a point where it co-awaits in, which means that in will take over. It'll retrieve a character and return it or yield it to out, and so on. So what we're going to do is we'll run out right away. So for coroutines, what that means is there's a special sort of function that controls this behavior, whether a coroutine function starts executing right away or it suspends right away. And so we will make out not suspend. It will run right away, and then it will automatically suspend at the first go await. But on the other hand, in will start out suspended, and it'll resume when out needs a value. And then the main program which drives these 2 coroutines, it will just simply call out. That's it. When out is done, that means your entire solution is done. Okay, so here's the compiler machinery. I am going to, I think, skip most of this, but you can look at it later. I think that, yeah, most of it is really boilerplate. Here's the in coroutines yield value function that is used to transfer the character from in to whatever needs it. Notice that the yield value runs when co-yield in the in coroutine is called. When that happens, it takes the value that has been read or retrieved, and it sets its internal state with a variable called val to that character that was retrieved, and then it suspends because something else is going to need this yielded value. And also note that the in coroutine always has a character ready, right? It doesn't need to wait for anything. It will call next char. Next char will call getLine if needed. And if getLine, if it's the end of file, then getLine will error out and there will be nothing. Otherwise, there will always be something in the buffer. So there's no need for the in coroutine when it's co-awaited to suspend at that point. So it's always going to return true because it always has something ready and available. Yeah, so this is again just compiler machinery for the out coroutine. You can see the initial suspend, which is saying return suspend never, which means that when out is first called, execute the body. Yeah, okay. So now let's go to the demo. How's the font size on this? Good? All right. So I've got the program here. Okay, so this is the entire program. Some comments in there that make it a little longer, but otherwise it's exactly what I showed you. Okay, so, and I've got a CMake file. Okay. In the CMake file, most of it is very straightforward. I'm using C++26 as the standard flag. I'm also, by the way, using a very, very new release of GCC. I don't need it particularly for this problem, but I have run into bugs that have been fixed within the last 2 or 3 months on GCC. So I would say if you're working with coroutines and you run into some issues, not chances are, but there's a good chance that it's a bug in GCC. So don't beat yourself on it too much. Go to GCC's Bugzilla and see if you can find any problems there. So if you're familiar with CMake, the way you set compiler options is through this statement or function, whatever, target compile options. So that's where I set the standard. And then I'm making sure that I have the debugging flags on. And then I've got this special flag over here, the special option. This is an undocumented option. This was introduced late last year, I believe, when it was accepted into master. And the motivation behind this, as far as I can tell, is that it's meant for developers, for GCC developers, because they wanted to understand what's going on with their support of coroutines. But it has a lot of value for ordinary users too. The problem with coroutines, one of the problems with coroutines, is that coroutines are like icebergs. The famous saying about icebergs that how much of it is visible above the surface? Like 10% or I don't remember. But there, that's what they say about icebergs is what you see floating above the sea is just a tiny percentage of the actual mass. And coroutines are like that. What you see is just, it's not as small as maybe an iceberg's top portion, but it can be comparatively pretty small. There's a lot of machinery that people have to write that's kind of hidden from the application. It's tucked away into these different data structures, a promise type, and a waiter, a waitable. So it's difficult to just look at a coroutine and decide, yeah, I know exactly what's going to happen or what this is supposed to do. Because you really do need to look at a lot of these other data structures to get a complete grasp, especially when you run into problems. But then the bigger problem is that when the compiler gets a hold of your source code, it transforms the entire function. And the result is generated code. And unlike templates, which are also generated, what's generated is not source code. So what's generated is sort of more direct intermediate code. So you will never see that source that's being generated that is your transformed function. And that means that when the transformed function runs, it's not your coroutine that's running. It's like, yeah, on the sort of visible effect side of things, it's the coroutine, but internally there's something very different that's running. So this flag, -fdump-lang-coro, and by the way, again, not only is it undocumented, it doesn't even come up when you do like GDB --help or there's no proof of its existence unless you go look at the source or you look at their bug tracker. But what this does is it dumps the intermediate representation of a coroutine. So it'll show you what the transformed function is and what the transformations are. Coroutines are a C++ standard. But the API is kind of small when you think about it. There's maybe a half a dozen functions that are directly associated with a coroutine, and then there's maybe like another 6, 8 things that are sort of indirectly associated. But there's a lot going on behind the scenes. Apart from this standard, there has been discussion that I don't think has been formalized yet of a coroutine ABI. So an ABI versus an API is an application binary interface. So to allow objects at a binary level to be compatible with each other. So there has been talk of a coroutine ABI. What that means is that there are certain internal representations that, if this is formalized, would be expected to be the same across compilers. And theoretically, that could mean that you could use like a library compiled, a coroutine library compiled with Clang with an application compiled with GCC. I don't know if this is ever going to happen. But this fdump-lang-coro will show some of those things. It'll show, how the layout is set up by the compiler and some things that do conform to the ABI. They're expected to be in a certain place, and you can kind of check that across compilers. Other compiler vendors, as far as I can tell, do not have an equivalent option to dump-lang-coro. So that's the first thing we're going to do. We're going to look at the output from this dump-lang-coro and examine that and see what we can glean out of it. So here we go. Let's do a CMake. Okay, so GCC 16, it's the next version of GCC. That's because it hasn't been released yet. And then let me do a make. Okay, so we've got our executable built. Let's see where the dump is. So I've got my build directory, and in the build directory, again, this is a CMake structure. If you don't know CMake, don't worry about it. But if you do know CMake, you'll recognize some of these things. So the objects are going to be in the CMake files directory, and yeah. So here we've got this, and then this. Okay. So this is the name of my source file, decoding string.cpp. It takes that name. For some reason, it attaches another .cpp to it. Then there's some number, alphanumeric, identifier. Not quite sure how they come up with this, but I think it's always going to be a 4-character identifier. And then at the end, you've got a .coro. So this is the output that fdump-lang-coro produces. Let's look inside. Okay, so here, again, big enough? Clear enough? It's good? All right. So it starts out with the original function. Remember, this is not code. This is the intermediate representation, what in GCC they call the tree representation. So this is the tree RTL. And because we asked for just the coroutine dump, there's going to be a lot of places in this intermediate representation where there's other kinds of intermediate or IR structures involved that are not going to be dumped, which is just as well, because it would get completely unwieldy if that were the case. So it's just the coroutine portion. So wherever there's something else that is not actually dumped, you'll see something like unknown tree or some kind of brief summary of what was there. But you can kind of make out what was there. This is the original function, but it's got some things changed or added to it. This thing is one of the yields. YD2 is the second yield. Over here is the first yield or the co-yield in the coroutine. Then you'll see some mangled names here. So for example, let's see. Yeah, so for example, this guy. This is a C++ mangled name for some type. This is an internal type. It's being dumped as part of the dump. This internal, or this line that I kind of highlighted over here, this is part of the ramp function. So you can read about the theory of coroutines and the design decisions or the design approach that was taken. But the ramp function is a term that's been used, not formally, but informally, to talk about something that sets up the coroutine. So it basically is in charge of creating the coroutine, allocating space for it, setting the variables internally for whatever will be needed when it's suspended, and then basically setting it up for the initial start. That's called the ramp function. And then down below, this is a good one. It shows the actual coroutine frame type. So this is just some annotation that's part of the dump. And this is the coroutine frame structure. So you can see that here, that's the type of the frame, the internal type of the coroutine frame. It's this mangled name, and then dot capital F frame. And this is kind of what I was talking about earlier in terms of a coroutine ABI. This coroutine frame has a portion that maybe will become part of a coroutine ABI, ensuring cross-compiler compatibility, possibly. The first field is this coroutine resume function. The second field is a pointer to a coroutine destroy function, and the third entry is the promise type. So these three things, from what I've read, have been discussed as a potential coroutine ABI. The rest is internal. The rest is implementation specific. So GCC will have something different than Clang, than MSVC for the remaining fields. But you can kind of guess what those fields are. So for example, the fourth field is called Coro resume index. And you can kind of guess that what this is referring to is that when a coroutine is suspended and then, it has control returned to it at some point, it has to continue execution at the point of suspension or right after the point of suspension. So the compiler somehow needs to keep track of where this was. So as far as I can tell, all compilers use some kind of indexing mechanism to mark those points first, and then there's some field or some kind of map that allows them to go back to the resumption index. And then there's some other stuff here. You can see this is the yield, the first yield or YD0. There's some data about that. So if you've got 4 co-yields in your coroutine, you'll see 4 YD type, YD named fields here, YD0, YD1, YD2, and then this last one is the final suspend. So, data related to the final suspend behavior. So that's just the coroutine frame type. The last piece, the piece that has the bulk of the responsibility is called the actor/resumer. This is a GCC-specific design. Even GCC originally had had separate actor functions and resumer functions. And there was some subtle distinction between them. But then they kind of felt like they're basically doing very similar things, which is to return, which is to take over when control returns to the coroutine, which can happen in many different ways. And so I think they merged it into this single function. If you have ever had the interest to design or implement coroutines in C, there's a thing called Duff's device that's used for that. It's very interesting. But it basically relies on some special behavior of the switch statement. And so any coroutine that you see, you can implement it using this switch mechanism, switch-based technique in C. And you can kind of see something similar happening here, right? There's the switch statement with different cases. Each one of these cases is like one of the suspension points and the resumption from there and so on. So it's kind of interesting to see that, how it's being implemented. Again, remember, this is not really C++ code. This is not any kind of language code. This is some intermediate code that is just a representation of what the compiler generated. Okay, so enough of that. That's the coroutine dump. So what did I want to show you? GDB. Let's get back to GDB. Okay, so as I said, things are really great if you're debugging coroutines in GDB right now in terms of features that you expect of functions. Like you step into a function, you break into a function, you expect to be able to see local variables. You can say info locals, it'll print the local variables. You say info args, it'll print the parameters. So all of those things work. But as I said, things that are special for coroutines or special to coroutines, those are still challenging. So one of the things I'd like to show you is how you can examine the state of a suspended coroutine, because that's something a function can't do. A function can't just go away and come back. When a function goes away, that is, there's a return from the function, it's gone forever, right? But a coroutine still exists. Now, where it exists is questionable. Typically, it exists on the heap. So what happens is that when a coroutine suspends, there's all this generated code that allocates some space on the heap, takes the coroutine frame object, the data structure that we just saw, updates all the variables, its state, whatever, and takes it off the stack, puts it on the heap. There's a little stub that's kept on the stack that is kind of a reference, two-way reference between this dynamically managed, dynamically allocated area where the coroutine now lives and the stack, so that there's some connection there that can be recovered. But it doesn't have to be that way. There is a kind of optimization. The compiler may decide that this thing can actually, that it doesn't need dynamic memory allocation. Not sure if it means that it'll stay on the stack somewhere, embedded, or there's some static area. Not 100% sure about that. But the point is that this coroutine can be anywhere once it's suspended. And you can't just simply say in GDB, BT for backtrace, and then change the frame and then expect to see, what's in that coroutine that I was looking at or that was running a few minutes ago. Can't do that. So you have to kind of work with stuff there. So let's run this program. Okay. And what I'm going to do is the program takes input on standard in. The triple left angle bracket bash feature, it allows you to use a string as standard input. That's all it is. So that you can kind of see the input right there on the command line. I've got a -S10 option to make the program sleep for 10 seconds before it actually does anything. And the reason is very specific to the environment that I'm using, which is Cygwin on Windows that emulates a Linux environment. On Cygwin, in Windows, GDB, you cannot run a program that takes input on standard inside GDB. You just can't. So you have to attach to it. So normally I would just say GDB, my program, and then there's a way that you can set standard in GDB, and it's much easier. But here I have to attach. So what I'm going to do is I'm going to run this in the background, get it SPID, and then attach GDB to it. Okay, so that's where we are, kind of. Let me set some breakpoints. Okay, so I'm going to list the out coroutine, some lines around the out coroutine. So out coroutine starts at line 239. Let me list maybe like 40, 50 lines from there. not, so I need something like 290. In GDB, you have to give line numbers. So I want to set my first breakpoint at the first go await, okay, which is line 257 here. So 257. So I want to break at 257. Okay, why am I breaking at 257? Because then I can examine the suspended in coroutine. On line 245, way at the top, you can see that I called in for the first time, which means that its initial behavior took over and the return object was returned. And we said earlier that we wanted a lazy evaluation of this in coroutine, which means we want to start it out suspended. So until the first go await, the in coroutine will be suspended. It should not be on the stack. So that's what I want to do. And so I set a breakpoint just before the first go await, and I'm going to continue the program, and it immediately reaches that breakpoint, right? It hits that breakpoint. So let's examine the stack here. Oh, by the way, let me just show you the things I was talking about that you can expect. So for example, locals to show the local variables. Yeah, that's fine. Out is a coroutine. You can see the local variables. What about the parameters? Yeah, it gets this hidden frame pointer, but it's being shown. If you know the frame pointer type, which we actually saw just a few minutes ago, we could look at this thing too. Yeah, so all of those normal things work. So now let's examine the stack. Okay, so here's the stack. Frame number 2, which is at the bottom, that's the main function, right? Then we called out, and now we're in out. So you can see the in coroutine is nowhere to be seen. It doesn't exist on the stack. As far as we can tell from the stack, there is no running or a function named in that is in any way, shape, or form related to the current execution. But it is, because it's a coroutine. It's somewhere on the heap. So how do we find it? So we do have the return object from in, right? So that was actually in one of the locals. Let me print that out. This is the return object. When you get the chance later, you'll see in the in coroutines return object, we stash away the coroutine handle that the in coroutine was created with. So this coro field that you're seeing, that's the coroutine handle for the coroutine. Internally, it has a pointer member, which is called _m_fr_ptr. This is the frame pointer. And we can use this frame pointer to look at the current coroutine frame, and it'll show us the state, even though it's nowhere on the stack. Now for that, I do need the, let's see if this just works. I don't think this will just work. I think I do have to cast it, but let's just see. Yeah. So I do have to cast this. No, sorry, that was a bad. What I want is coro dot. In, yeah. I need in, then coro, then it works. Okay, so let's see if this, yeah. So this is basically a void star right now. So I do need to cast it the correct type in order to see the coroutine frame. And for that, I'll have to go back to the dump. Let me open up another window. Okay, so here I want the frame type. This is the frame type. This is mangled, but I can use it as is. Okay. Oh, what's going on? All right. Let's see. So I'll need to dereference this thing as a pointer. I think that should work. Syntax error. Yeah, okay. So I think we need the quotes around the type because of that dot in there. That's kind of not typical. But now I took that void star opaque pointer and cast it to the right type, and we can see the coroutine frame, even though it's nowhere on the stack. This is the in coroutine. And you can see the first three fields. The resume function is set to something inside the in coroutine, some code over there, the destroy function, the promise. Some of these values don't make a lot of sense to me, like why does frame needs free? Why is that true right now? But maybe it's just some value that is not needed right now. It's set at some point later on. But yeah, so that's one way you can look at a suspended coroutine. Now, almost out of time, but what about async call stacks? So you'd need to do something similar to this. And as I mentioned earlier, the challenge there is that if you're just using generic coroutines, you're not doing anything special or custom in terms of supporting this examination later. Things go through the standard library, and it's not that easy to figure that out, how that connection is maintained between a coroutine that's suspended and its place on the stack, where it'll eventually belong again. What you can do, which is, libraries like Folly and some other projects have done, is that they maintain special variables inside the promise of the coroutine that allows them or helps them later on to figure this out. Generally, they're called continuations. But essentially, what you're trying to do is you're trying to, at the point of suspension, you have this information, or at least you have control over this information. What you can do is, at the point when you're going to be suspended, you as a coroutine, you are told where you will end up. You can choose to ignore this information, but you can also use it. So store that away in a promise, in your promise, and then later on, that's available to you. And then you can sort of thread these connections, because it's not simply that one coroutine that's suspended is directly connected to the stack somehow. It may be that the coroutine is connected to some other coroutine that's, it's like the control may not be transferred directly to something that's on the stack. So you do need to sort of wend your way through this thing, and you can do that if you're aware of the need for this information later on. Yeah, so I think that's about it. I hope it wasn't too disappointing. Like, you know, I wish I could tell you that there was a GDB coroutine feature that you could just say, GDB coro, show me the stat, show me whatever of this coroutine. Like threads, right? GDB has a whole bunch of, there's a huge feature set related to threads. You can switch between threads, you can look at their call stacks, you can do all sorts of things. Why not for coroutines? I've read some documents that suggest that LLDB, which is the debugger for the Clang project, does have something like this, but I haven't had a chance to use it. And you know, most of the world still does use GCC and GDB, so while that's helpful, you know, in terms of just general knowledge, it may not help you enough with a specific problem. So yeah. Well, thank you very much. I don't know if we have time for questions, but I'm available after. That's it.